Okay, this recording we're going to solve one of the questions in the review, which is a multiple choice question. Which of the following is the basis for P4? In a chapter on 4.6, we know that the dimension of Pn, the space of polynomial degree n or less, is n plus 1. So therefore, the dimension of P4 has to be equal to n plus 1, 5. So with that, we know that a basis of P4 must have 5 elements. So you see that the question has only 5 selection, but I add a few more to explain to you which ones are actually the possible basis for P4. Almost right away, we can tell that A cannot be the correct answer. A cannot be the correct answer because it only has 3 elements, so this is out. B, 1, 2, 3, 4, 5, 6. No, that cannot be the correct answer. C, 1, 2, 3, 4. Almost there. No, that cannot be the correct answer. D, 1, 2, 3, 4. That cannot be the correct answer. And so we know just by counting that probably E is the correct answer. E has 1 polynomial, 2 polynomial, 3 polynomial, 4 polynomial, 5 polynomial. So E is in fact a basis for P4. But I added F, G, and H because these things are more interesting. They all have the correct number of elements, but are they bases? Let's look at F. 1, 2, 3, 4, 5. Wait, it has 5 elements. Why is it not a basis? Well, if you have to test it, it's probably not a basis because it doesn't have t to the 4. It doesn't have t to the 4 here, it doesn't have t to the 4 here, it doesn't have t to the 4 here, and every term doesn't have t to the 4. So no matter how well you take linear combination, it could never come up with t to the 4. So for that reason, the span of this set of vectors cannot be a basis for P4. So the span does not contain t to the 4. So this is also not a basis. And remember what it means to be a basis. To be a basis means that firstly, it has to span the vector space, and secondly, they have to be linearly independent. But because we have an extra information that the dimension must be 5, this set is probably linearly dependent. Probably. Yeah, because it has the right number of elements, but it's not a basis because it's linearly dependent. Alright, what about this one here? 1, 2, 3, 4, 5. It has 5 elements. It also has t to the 4 somewhere here. But the question is, can we just get t to the 4 by itself? Is it possible to take linear combination of these elements and yet get t to the 4 coming out? The answer is no. T to the 4 cannot be linear combination of these guys because when you take this thing together with all the other thing, t cubed doesn't get cancelled away. Unlike this one, you can actually have this thing minus that thing, and t cubed, t squared, t, and 1 all will cancel away. So this one has a very deep reason why it is not a basis for P4. It is slightly harder. So no, this is still not a basis for P4 because T4 is not in the span. It's not in the span of G. So this is also no. No. Now this one is very interesting. T to the 4 is already there. And then you can ask that question, maybe t cubed is not there. So is it possible to get linear combination of these things and then come up with t cubed? The answer is yes. Okay, this one is slightly harder, but this is a basis because if you're very clever, you can get t cubed. You see, taking this and this together, a linear combination of this and this, for example, half of this plus half of this is exactly 1. Right? So if you take that thing and add to half of this and half of this, you get exactly t cubed. So this is slightly harder. But This is how you know whether something is a basis. Not just that it has to be span the space, it has to be linearly independent, but knowing the dimension does help us know the answer a lot faster.